After the last video, you may be wondering, how in the world can I know when to apply the Cottrell equation with all the things that could go wrong? Well, this video answers that question for you. How can I tell if the Cottrell equation is valid? Well, first, let's notice that our current is proportional to 1 over the square root of time. You can see that kind of response here on the right in the plot. If I plot that versus 1 over the square root of time, sure enough, I get a linear line. This is my first indicator that, hey, I think the Cottrell equation may be valid here. However, I caution you not to stop here, because if we take a look a little closer, we may see that it may not apply over the entire time range. If I take the log of the Cottrell equation, you can see that I get the log of my current over here, log of the Cottrell equation right here. I can use some logarithm rules to break this down, and then I treat my log of t as my x and my log of current as my y. My y-intercept will be everything else from the Cottrell equation, and my diagnostic here is the slope. Here in the plot on the right, you can see that the light blue line is my linear line with a slope of negative 0.5. And we can see that here at long times, we are not adhering to the Cottrell equation. Now this data is for the reduction of chrome 2+ to chrome metal. And so I'm forming an insoluble product. I could have surface area growth or natural convection or both causing that deviation here at longer times. However, I can see at short times though, I am keeping to that negative 0.5 slope. This is the time range over which I want to analyze. 10 to the -2 to about 10 to the -1 seconds is where I want to analyze my data. So there's two approaches I could do at this point. Is I could do a nonlinear fit to the Cottrell equation, or I could use the y-intercept to calculate my diffusion coefficient or my concentration, whichever one I want to rearrange for. The nonlinear fit is a better way to do it because it likely results in lower error, because whatever error I have on my y-intercept, it's being exponentially increased because to transform it to calculate the diffusion coefficient, I have to do 10 to my y-intercept. But a caution here, when I take this data for the copper deposition onto platinum from the previous video, and I do the log plot, I can see how at these longer times, I start to get a slope of negative 0.5, because here you can see the Cottrell equation being plotted right there. And then, but if I extend the line for the linear fit to my data at negative 0.225 volts, I can see that I get the same slope, but I don't get the same y-intercept. Here is the y-intercept that I'd get for the Cottrell equation. And here is the y-intercept that I'd get for the fitted line to my data. Even if I get the negative 0.5, I could still be off a little bit. But doing the diagnostic of the log plot helps increase your confidence that the Cottrell equation may apply, but you may want to be wary of chronoamperometry data for a deposition of an insoluble product that may have nucleation that could throw things off. All right, that's it for the diagnostic tool. In our next video, we'll be taking a look at microelectrodes and surface roughness.